Okay, now, next thing we're going to do is we're going to discuss the dot product, which is another operation between vectors. And so back to our notes, and here we go. The dot product. All right, so the dot product is a very useful and important tool. So first off, what is the dot product, you might ask? And so the dot product of two vectors, u and v, let's say, is given by the sum of the products of the corresponding components. In other words, u dotted with v is going to be u sub 1 times v sub 1 plus u sub 2 times v sub 2 plus u sub 3 times v sub 3. And the dot product, notice, is denoted by, well, putting a dot in between the two vectors. It goes in the middle of the between the two vectors. So pretend that that's centered vertically. All right, so in 2 dimensions in R2, pretty much the same thing, except that we just have a slightly shorter sum, right? U1 plus times V1 plus U2 times V2. So what are some properties of this dot product? Well, the dot product is kind of cool because it kind of acts just like, in terms of properties, like regular multiplication by a scalar, more or less. The dot product of u with v is the dot product of v with u, so it's commutative. It's also distributive. So if I have u dotted with v plus w, that's u dot v plus u dot w. And if I have a constant times the dot product of u and v, I can multiply either vector by the constant first and then take the dot product. And finally, the magnitude property, which is not necessarily very intuitive on its face, is that the dot product of a vector with itself is the norm of is the magnitude squared. So let's check and see that that makes sense. So what is the dot product of a vector with itself? So I'm going to have v1, v2 dot v1, v2. So that's going to be v1 squared plus v2 squared. And since the magnitude of v is the square root of that, this gives us the magnitude of v squared. Okay, so let's do a simple example. Let's suppose we have 3 vectors, p, q, and r, defined as on the page. Let's find 2 times the dot product of p with q. So we could do this a few different ways. I'm just going to directly find the dot product of p with q first. So I'm going to have -1 times 0 plus 2 times 18 plus 3 times -3, which gives me 27. All right, so 2 times that is 2 times 27, which is also known as 54. So that is 54. All right, what about the magnitude of -3 times r? Okay, so first let's compute -3 times r. Wow, so that's going to give me -3, +3, -3. So the norm of that vector we just constructed is going to be the square root of -3 squared plus 3 squared plus -3 squared, which is the square root of 27, also known as 3 times √3. Is this what you expected? Did you expect this? Did you think it was going to be something else? Another way to think about this, now I'm drawing a blank if we actually cover it, is to also think about the magnitude of -3 times r is really, well, it's the magnitude of the scalar times the magnitude of the vector. Well, the magnitude of the scalar is just its absolute value, and the magnitude of the vector is going to be the square root of -1 squared plus 1 squared plus 1 squared, which gives me 3 square root of 3. So it's another way to get the answer. Now, another cool, important fact about the dot product is that it satisfies this equation. The dot product of u and v is actually the product of the magnitudes of u and v times cosine of theta, where theta is the angle between u and v. Where does this come from? Well, this comes from thinking about making a triangle with u, v, and v minus u. And so if we were to construct that triangle, think trigonometry, right, we would know that the three sides satisfy the norm of v minus u squared is norm of u squared plus norm of v squared, or magnitude. Sorry, I keep saying norm. Norm and magnitude mean the same thing for our purposes. Minus 2 times the magnitude of u times the magnitude of v times cosine theta. That's just the law of cosines or trigonometry, or however you want to say it. And so now what? Well, let's do this. Correctly would be nice. So the magnitude squared from above, we know that that's just the dot product of the vector with itself. And now we can use the distributive property to rewrite this a bit, v minus u dot with u, which is v dot v minus u dot v minus v dot u, the quantity v dot u minus u dot u. So I get v dot v minus 2 u dot v. Well, let me go a little bit slower and write all the middle steps. Distribute the negative sign. Okay, so what do we know from, we know that the u dot v is equal to v dot u. We know that v dot v is the magnitude of v squared. And u dot u is the magnitude of u squared. And so if we plug that in to that equation, we have magnitude of v squared minus 2 u dot v plus magnitude of u squared is equal to, we have the right-hand side, which was the magnitude of u squared plus magnitude of v squared minus 2 times the product of those magnitudes times cosine of theta. And stuff just does us a favor and says, see ya, it gets canceled. I'm left with, let's just divide both sides by -2, right? So I have -2 u dot v is -2 times magnitude of u times magnitude of v cosine of theta. And then, like I just said, let's divide both sides by -2, because good old algebra tells us that we get to do that. And we get, u dot v is magnitude of u times magnitude of v times cosine of theta. Now, big deal here. is that we can solve for cosine theta. Okay, well, from the equation, that might not be like, woohoo, big deal, but it's kind of a big deal, right? So we get cosine of theta is going to be the dot product of u and v divided by the product of the norms. Now, remember also that we're considering the smallest angle between the vectors, and so theta has to be between 0 and 180 degrees if we're doing degrees, or between 0 and pi in radians. Keep in mind that we usually are using radians in this class, so we're usually using radians. So why did I say this was a big deal? Well, we could tell if two vectors are orthogonal, right? For orthogonal, think perpendicular at a right angle. And how do we tell that? Well, if two vectors are orthogonal, right, what's the angle? Right, the angle has to be 90 degrees, right? And so, boom, that means that the dot product is going to be 0. So if the dot product is 0, that means that the vectors are orthogonal. Okay, let's go. Apparently that says 1 instead of A because, well, I'm not perfect. Okay, let's find the angle. Let's take this vector u, 1, negative 2, 2, and find the angle between that vector and the vector v, which is 0, 6, 8. Well, that's pretty straightforward, right? From equation 8 up there, we know that cosine theta is equal to the dot product of u and v over the product of those norms. So the dot product of u and v is 1 times 0 plus negative 2 times 6 plus 2 times 8. And what about the norms? So the norm of u is going to be the square root of 1 squared plus negative 2 squared plus 2 squared. And the norm of v is going to be the square root of 0 squared plus 6 squared plus 8 squared. So if we do all the work, that's going to give us 4 over 30, also known as 2/15. And so theta is the arc cosine of 2/15, which is approximately 82.34 degrees. I know, I just said that most of the time we're going to use radians. We really will, just not for this example. That was total calculator work. I mean, you can imagine this isn't something that we have memorized. Okay, second problem. We want to find a vector w that's orthogonal to u. Okay, so let's let w just be something we have no clue, which is pretty easy to do because we have no clue. So we have w1, w2, w3, and we need the dot product of u with w to equal 0. But the dot product of u with w is 1 times w1 plus negative 2 times w2 plus 2 times w3, which gives us w sub 1 minus 2w sub 2 plus 2w sub 3 is equal to 0. Or we could solve for w1, which tells us that we have a whole lot of vectors that satisfy that. In fact, infinitely many, but we just need to find one. So let's just pick w2 equal to 1 and w3 equal to 1. And then w sub 1 is going to be 2 times 1 minus 2 times 1, also known as 0. So my vector w being 0, 1, 1 is orthogonal to u. It's orthogonal to u. But this is not even the most exciting or important aspect of the dot product, believe it or not. Oh, I should mention, little definition thing first. The angles formed by a non-zero vector and the unit vectors, remember the unit vectors, those are called direction angles for the vector, and the cosines for those angles are called the direction cosines, and the textbook has a nifty little picture reproduced here, which shows that. Now, here's the important thing I was going to talk about. We can use the tools we have so far to define something really important. It's called a vector projection. Why is that super important? Well, think about a vector projection right now as the shadow cast by a vector in a certain direction. So let's suppose, for example, we have a vector in R2, coincidentally with a little picture right here on the right there. And the projection, let's say along the x-axis. So I've got a vector in R2, you know, I draw my little vector, and then I look down straight above. And when I look down, what happens? What happens is I have this shadow cast here. That shadow that's in that red vector, that is the projection along the x-axis. But more generally, right, I can have a vector u and a vector v, and I can define the projection of v onto u. And how do we do that? Well, let's suppose that this is theta here. Okay, now using geometry, right, we know that v is more or less our hypotenuse, and so the projection of v onto u is going to be the magnitude of v times cosine of theta. And then cosine of theta is just the dot product of u with v, but we're looking at the magnitude of the projection, so we have an absolute value there, and then divided by the norm of u, and then we just multiply this norm by some unit vector in the direction of our vector u. So basically we take, what's a unit vector in the direction of u? Well, that's just u divided by its magnitude. So putting that all together, the projection of v in the direction of u is going to be, well, this u dot v divided by norm of u, the magnitude of u, times u over its magnitude, also known as v, that the projection is going to be the dot product of u with v over magnitude squared times u. And that's equation 9. The length of this vector is the scalar projection of v onto u, right? So we're not actually multiplying the norm itself, right? We're just multiplying sort of the direction of the norm. Okay, let's do an example, and then we will call it a recording. We want to find the vector projection of v given here onto u. So step 1, just calculate stuff, right? All right, so just plug and play from the formula. Projection of v onto u is going to be the dot product of the two vectors divided by the norm of u squared. So that's the square root squared, which just means that we're looking at u squared, this 4 squared plus 4 squared plus 4 squared times the vector 4, 4, 4. The first quantity is a scalar, so it's just a regular scalar product. Okay, so that gives me 1 times 4 plus 2 times 4 plus 1 times 4 divided by 64 times 4, times our vector 4, 4, 4. So what does that give me? 4 plus 8 is 12, 12 plus 4 is 16. By the way, 4 squared plus 4 squared plus 4 squared is 48, not 64. So let's fix that. So we get 16 over 48 times 4, 4, 4. But we know 16 over 48 is 1/3. So I get the vector 4/3, 4/3, 4/3. And you might want to try to sketch it to see that this really is what you get. Again, suggested exercises as usual, and next time we will be doing the cross product. Okay, hopefully you found this video helpful and have a great